It is twice.
I'll check right now.
Okay. But hold off. One more and I'll show you and then you guys can, I'll give you time in here. Okay, so this is example 6.3, but I looked in there and I thought I'll just put in all the details so you know exactly what's going on and it'll really help you, I think, with the homework. So in this one, they have, it's a joint distribution function. So they give you two random variables. And I don't know, they said a random sample of n equals 2, which seems awfully small, but I wrote down what they said, and they said it's coming from the uniform distribution. So I feel like, I could be wrong, I just glanced through your homework, I feel like there's something almost identical to this problem on your homework. So that's the first one you have to check out today and see if you can run through it. So what does that mean? They didn't give me this. It's the definition of a uniform distribution. So that's the Colonel Watt style, right? You didn't tell you that. You're supposed to know that from the definition of uniform distribution. So this thing pulls out F1, the marginal distribution for the first variable is 1 on that interval where it has support, and then 0 elsewhere, and F2 is this guy. So that's not given. That was my addendum. Keep laptops closed, please. So I'm highlighting this for you because there were a lot of questions on the last homework where you, and in fact, when I wrote up the feedback, some of you like actually put in there, I don't know what function I'm supposed to put in here. So this comes from the definition of uniform distribution. And how do I know that it's 1? Because it's the area of this interval. Well, it's a length in this case. So 1 divided by the length of this interval is 1, so it's 1 divided by 1. You guys had the circle of radius 2 for your other problem. What would be the area of that circle? 4 pi. So your uniform distribution would be 1 over 4 pi. So again, this was not given either, but these are independent variables because they were randomly selected. So your joint distribution, your joint PDF is given by 1 where y1, y2 are belonging to a box of size 0, 1 with length 0, 1 and 0 elsewhere. So that's the region of support. So Colonel Watts always says to draw the picture. And I actually, she probably was a great student all her life. I wasn't. So I think some of the things I tell you was because I wasn't a great student all my life. It's hard to believe now, but I was a terrible student as an undergrad. So I would never draw the picture. But I remember like when I first went to Georgia Tech and I taught these classes that you're taking now, I thought, well, I had to prepare for the lectures. And I thought, wow, it's so much easier when I read the book and when I draw the pictures. So I had to kind of get that for myself, even though my teachers always hollered at me to draw the picture. So I'm telling you, don't do what I did. Draw the picture because it makes it a lot easier to see what's going on. So what they want you to do in this problem is they want you to find the distribution function for u equals y1 plus y2. Benign looking problem. It's not though. So the first step is like before, you're finding the new boundaries. But now you've got a big mess because you have to draw the square out and then you have to draw what y1 plus y2 equals u looks like. So you're really looking at the set of points y1 plus y2 are less or equal to u. So this is your boundary right here. Yes, it's the same boundary you guys talk about in real analysis. You're looking at the boundary of a region. Except you haven't gotten to multiple dimensions yet. So if I just draw a picture, and unfortunately you can't just draw one picture here because you have to look at all cases, but I just drew a picture of y1 plus y2 equals u for an arbitrary u. This is in your book. It could actually be anywhere. It could be slicing like this. And so the region of support would be underneath here actually. Because this is the region of support you want underneath here, so it would be right in here that is your region of support. But the line doesn't have to be there because u could be any number. And so the line could be here, the line could be here, and the line could be up on top. That's another place you could have it up on top. So you kind of have to look at all cases when you map it out. So when you draw this thing out, so Colonel Watts is saying, well, these are straightforward problems that she's given you for homework 4. So she's like, I'm going to give them a little breathing room. Like, But actually they're not, because you have to sit there and draw these pictures and think about everything. It's like different kind of pain. I always get worried when she says, oh, I'm going to give you some breathing room, because I don't think she's that tight. Boundary depends on you. So you're going to set up each of the cases. So case 1 is that u is less than 0. So you have to draw that picture up, and it's the intercept that you're looking at. Let me go back to this picture. So in this case, the intercept of this y1 plus y2 is equal to u. The intercept is u equals 0. So if it's u is less than 0, it's going to be down here. If it's u that's, what's this point right here? The intercept would be 2, right at that hook, right? Because 1 plus 1 is 2, and then if you scale it back this way, you'll get 2 as your intercept for this line. So everything greater than 2 is going to give you a different picture. And then you have different slices that you can take in here as well. So I did the easy ones first, because I like to avoid the uncomfortable questions, as I just pointed out to you. So it made me uncomfortable to think of the inside the region, so I went outside the region first. So outside, the first one is u is less than 0. It's underneath there. Well, in there, the function has no support, so it's 0, so I don't need to do anything. The other one, it's bigger than 2. How do I know that this is 2 here? Well, that's the intercept that you're going to get right at 2. And then everything goes up to this point. In this region, what would the distribution function have to be? 1. I can do the math, but you know the answer is 1 outside of above that region. So we can no longer avoid the hard work. It's right here. There's 2 of them. You could have this little triangle underneath here. You can actually calculate the area of this triangle, and eventually I do, because I got so annoyed with having to calculate these integrals. But as this purple line slides up across this region, you don't just get a triangle anymore. Right here you get 2 regions, actually. You get like a parallelogram and something like a triangle underneath. And so that's kind of when I quit and said, I'm just going to use geometry. So you guys had a weird region, too, in one of your homeworks from the last problem, where you could do it by cutting it up into pieces. So this is a double integral, if I want to calculate this thing. This is u between 0 and 1, because this purple line stops being a triangle right as it hits the intercept 1. Got it? Are you just guys nodding your head, or I'm explaining okay? All right, so if I do my integration, I shoot the arrow, y2 goes in at 0, y2 goes out at the formula for that line, which is u minus y1. Those intercepts, that's going to be y1 equals 0 to y1 equals u. That's the intercept of this equation right here. Right, that point right here is y1 equals u, where it stops. And by the way, that's not given to you in the problem. You have to kind of figure those things out. U minus y1. So I actually had u minus y2 because the book had something like that. And I was looking in there once in a while, and I thought, wait a minute, they're doing it different than I am. So I'm just going to leave it alone. So that's u minus y1. It cannot be y2 because the limits are y2. So you do the integration, and it comes out to be u squared over 2. So interestingly enough, I think I did all of them different than the example in the thing. So at the end of the day, you're looking back and look at the answer in the back of the book, matched up. The book is right again. All right, so that's the last picture you have. So you could do this as an integration, like I did before, but you're going to have to break up the regions. You have the triangle region, and then you'd have what's left over from the triangle, and I don't like that. So I decided not to do that. So there's no way. I'm not going to do like 4 integrals in pieces like that. And I guess you could use symmetry and maybe avoid some of it. But what I did is I just decided to use geometry. And I don't want to figure out, like I don't even like geometry. So I'm not going to figure out the geometry of this one. I'm just going to figure out the area of that triangle at the top and then subtract it from 1. So the total square area is 1. The uniform distribution function is 1 in there. So it's not like I'm just calculating the area of that region. This area that up at the top, the red one, is actually easy to calculate. It's a triangle. The formula for area of a triangle is 1/2 base times height. So I literally have to just look at where those connector points are and figure out the base and the height. So here's what I did. From here to here, you have y2 is equal to 1. And this point right here is the point on the line. So the shaded length I have there is y2 is equal to minus y1 plus u, because that's the formula for the line. And y2 is 1. Let's see. So it's the teal length I really want. The whole length across is 1. So it's 1 minus that shaded length, which is minus y1 plus u. Subtract that off and I get 2 minus u. So I'm just looking up there and saying, where does that point at the top come from? This point right here. It comes from being on the line. So I just plug those things in the line, and I set y2 is equal to 1, plug that into the line. Why am I allowed to do that? That's where they intersect, that's y2 equals 1 there. So I put y2 equals 1 into the formula for the line, and I get this 2 minus u. Then I calculate this height. That's just y2 equals minus y1. Again, I'm using the formula for the line, but in this case, y1 is 1, so I plug in y1, and I get y2 is minus 1 plus u. So this green area is 1 minus that, because the whole stick is length 1. Subtract off the green part, and I get this top part here turns out to be 2 minus u as well. So it's a isosceles triangle. Two sides are the same. So the area of that red triangle is 1/2 base times height.
Then you could integrate just the area of the triangle and subtract that -1.
You could do that too. Yeah. I was already going down this path. And so I get the area of the red triangle is going to be this guy. I expanded it out, and I didn't even use Mathematica for that. And the area of the green region would be 1 minus that 1. So it gives me this thing. I made it look probably worse than it was because I was actually trying to tell you where I got everything. You wouldn't probably do all that, just you find where those points are and just plug them in. So I crank it out into this distribution function, into the pieces. This is the one I just got by the triangle thing. The one I got before, and then 0 and 1 on the outer edges. And then the last step is to find the derivative in pieces. And there's the PDF for this guy. And I think there's one, she mentioned there's one that you have to do like maybe polar. So if you start changing these regions, they start getting, this was just a uniform distribution function on a square. So it's not like it, and it was all these multiple little cuts that I had to look at. So it's not that trivial, I think. It's a different kind of pain. Like the other kind of pain is you have to sit and think somewhere. This one is where you have to sit and actually draw things out.